Hi, I'm Maarten and I want to explore how a computer would solve a geometry problem.
Say we want to know which points in a set are on the outside.
Well, first question, what do I mean by the outside?
A point is on the inside if it is completely surrounded by other points. So it's on the outside if it's not.
Oh, clear? Good.
So how do I know which points are on the outside? That's easy, right? I mean, we can just see it.
Well, yes, we can, but computers can't. Computers are kind of like blind people.
How would you do this if you were blindfolded?
So we couldn't see all the points at once, but we could still examine and compare individual points. So rather than seeing the set as an image, we can represent each point by a pair of numbers, its x and y coordinates, and store each point in a cell.
Now I've got this nice stack of cells, and every cell contains a point, and I can open one cell and look at the point that's inside. Alright, so given this set of points, how do I find out which ones are on the outside?
Well, let's just get started and try something. And to keep things interesting, let's put on a timer so we know how long this whole thing takes. Ready? So, since I'm not supposed to know anything about the points, let's start by shuffling them just to make sure that they are in completely random order. And then let's take the first point and try to find out whether it is on the outside or on the inside. I'm going to generically call this point A. And I'm just going to write that down to keep track of what I'm doing.
Okay, so if a point is on the outside, it must mean that all the other points are kind of on the same side of the first point.
And to find that out, we will obviously have to look at the second point too. So let's call this second point B.
Okay, so maybe to keep track of these points, we should make a second copy. They may have different colors, but deep inside they're the same.
So once I have 2 points A and B, I can imagine the concept of a link, a segment connecting the 2 points, right? So from A to B, and I can imagine this concept without looking at those points. But this is still not enough information to tell me whether A is on the outside or not. All points should be on the same side of A, but what is the side of a point? I need some sense of orientation.
So how about we just try all possible links and check if they're on the outside?
Well, a link is on the outside only if all other points lie on the same side of the line that extends this link. If all the points are on the same side of this line, then this link is on the outside. So let's take a third point and call it C.
Maybe we should copy those points once more.
Let's take that third point and also consider the segment connecting the second to the third point.
Okay, so now I have 3 points. Let's say 3 points just fits in my memory. I can remember the coordinates of those 3 points. So now I need to figure out whether the third point lies to the right or to the left of the line through the first 2 points.
Well, this we can test. We just consider the links from A to B and from B to C. And now we measure the angle at point B. So at this point there are 2 possibilities. So either this angle ABC turns right or it turns left. So in this case it turns right. So what does that mean? Well, it means that my third point C lies to the right of the line through A and B. So it could still be that AB is a link of the outside. So I should now just check the next point C. And as long as I keep finding point C that also lie to the right of AB, I continue.
So AB is going to be on the outside of my point set only if all possible points C lie on the right of AB.
Now the other option is that C lies on the other side of my line through A and B. It turns left. If that's the case, then this means that link AB is not on the outside of my set. So it could still be that A is on the outside, but I would have to pick a different B. So in this case, I should discard B and check the next point B. And for this new B, I again have to look at all possible points C to find out whether they all lie to the right of AB. Every time I find a point C that does not lie to the right of AB, I take the next B and I start again with the first option for C. Of course, it could happen that I run out of options for C before I find one that does not lie to the right of AB. Still follow me? So what does this mean? Well, it means that I run out of options for C before I find one that does not lie to the right of AB. Well, that means they actually do all lie to the right of AB. And so that means that my link AB is actually part of the outside.
So it looks like we're fine. Every point, every possible choice for C lies to the right of the line through the point A is 2,8 and B is 3,10. So this means that the segment from 2,8 to 3,10 is confirmed to be on the outside of our point set.
So AB is on the outside. Great, so now I've definitely decided that my first point A is on the outside. Now I just need to do the same for all the other points. So while I do that, you may wonder how reasonable it is to say that I can measure the angle between 3 points. If I cannot see the points, then how can I draw the segments connecting them and measure their angle? Well, a computer would not actually measure the angle with a physical protractor, but rather would calculate the determinant of a small matrix involving the coordinates of A, B and C. But this is a simple calculation that only involves 6 numbers, so a computer can do this really fast. Of course, it could also happen that I do not run out of options of C for any choice of B, and instead I run out of options for B. So what does this mean? Well, it means that for all options of B, there is some point C to the left of AB. So that means that A is in some sense surrounded by other points. In other words, this is a proof that A does not lie on the outside. We discard A and continue with the next one. And while I have fun with that, you may be wondering why I am only testing whether all points C lie to the right of AB. Because wouldn't it also be fine if all points C lie to the left of AB? However, I can safely ignore this possibility because I'm testing all possible segments AB. And so if all points lie to the left of AB, they all lie to the right of BA. So I will discover this when I'm testing A is B and B is A. If you're still following me. If not, don't worry, just sit back and relax and watch me executing these steps. Eventually, we run out of options for A and we're done. So, we were able to correctly determine the outside of a set of 10 points in 3 hours, 49 minutes and 5 seconds.
I'm quite happy about that result. So you might say, Martin, that was a pretty stupid thing you just did. But remember, computers are stupid. They just blindly execute any orders you give them. This works. This correctly figures out which points are on the outside. It just took a really long time. Let's try to do this in a smarter way. So let's reset the clock. And just to be fair, let's start by randomizing the points again. But actually, wouldn't it be more useful if the points did not come in a random order, but let's say from left to right? What if we add our points from left to right, keep track of the links so far, and repair them when we need to? And then maybe we could use that information to be more clever in our selection of which points to test. Alright, so maybe we should start by sorting the points from left to right. Okay, so at this point you may wonder, if I can't see, then how can I possibly order my points from left to right? Well, how to do that is a whole separate subject, which I'm not going to get into here, but I'll just mention that what I'm using here is the famous quicksort algorithm, which is basically a quick way to sort things. And in this case, it just takes 6 minutes and 15 seconds. Alright, so now that my points are sorted, I know that the first point I'm going to get is going to be the leftmost one. And so certainly the first point I get will be on the outside. But then how do I know whether the other points will be on the outside or not? So I'll use a very powerful idea here. Instead of building the whole outside at once, I will start by just computing the outside of the first point. Not very interesting, it's just a single point. But now I will add my points one by one, and whenever I add a new point, I will update or recompute the outside of my points so far. Okay, so the outside, so the points that will keep growing, and more points get added. Whenever I encounter a point which is no longer on the outside, I will just throw it away. So here all my points are still on the outside, then I get the fourth point, and at this point I realize this guy is not on the outside, so I throw it away. And then I look at the next point, everybody is on the outside, I find another point and I realize this point is not on the outside, so I throw it away. Now for this to work, I need to know that if a point is not on the outside of the first few points, it also will not be on the outside of the whole point set. Otherwise, I will have thrown away a point that I might still need later. But this is clearly true. If a point is on the inside of my set, then it means it's surrounded by other points, and if I add more points, well, sure, that surrounded point is only going to get more surrounded. Okay, so let's get started. So let's just put all points which I have currently processed and which are on the outside on a stack. And now to find out whether my stack is correct, I am going to look at the top 3 points on my stack. Well, if there are no 3 points in the stack, then obviously all points in the stack are on the outside. So I just continue and add the next point. So if there are 3 points on the top of my stack, I can simply test whether the angle between those 3 points is turning right or left. If this angle is turning right, then everything is fine. Then I know that all points in my stack are on the outside because I knew that before I added the last point, all points were on the outside. If the angle ABC is not turning right, then I know that B is not right. It doesn't belong on the outside. The line through A and C
passes over B, so I should throw away B. And now at this point it is important not to proceed with the next point yet, because, well, I've just thrown away a point from my stack, but I have never tested the angle between the previous point in my stack and the current top 2 points. So this turning angle could also be either turning left or right, and if it's turning left, then this point would also have to be thrown away. So I don't proceed, but rather I go back to the test where I take the top 3 points of my stack and test their angle. And then when I find an angle which is turning right again, I continue and add the next point. And while I do that, you may wonder, well, why am I only testing whether ABC is turning right? Because if ABC is always turning left, then I would also find a piece of the outside. It would just be the bottom half instead of the top half. And that's a good point. And in fact, I'm only going to find the top half of the outside. And we're done! So now we have a nice stack of points, or rather a stack of cells which contain points, which are exactly all points on the top half of the outside.
Okay, so admittedly this is only half of the outside, but the other half just works the same. We can just turn the world around.
We flip everything. We just replace the x coordinates by minus x and y by minus y, and the computer will know what to do. And while we watch me having even more fun, you may wonder... actually, at this point you're probably done wondering. Let's just get this over with. All done! Using this second approach, I also correctly determined the points on the outside. But this time it only took me 41 minutes and 18 seconds.
So now for the conclusion.
This one is a bit slower and this one is faster.